Alors, bonjour tout le monde, merci d'être là en présentiel, ça fait plaisir de voir beaucoup de personnes qu'on a vues seulement dans des petits rectangles ou seulement dans des petits rectangles avec des petits noms. Il y a probablement des gens qui vont continuellement rentrer parce que c'est un petit peu compliqué à trouver la salle. Au cas où, nous sommes à Amphipôle 340, s'il y a quelqu'un qui est en train de chercher sur Zoom. Alors, c'est un très grand plaisir de commencer cette nouvelle série du séminaire Climate. You're going to be presenting in English.
Yeah, I'm presenting in English.
So I should be speaking in English as well. So welcome to a new semester of the Climate Seminar Series. So thank you, everybody. Thanks for having connected. And it's a real pleasure to start this new semester of the Climate Seminar Series. I think this is now our third year that we're doing this. Which is an interdisciplinary seminar series on the topics of climate quite generally. And it's especially a pleasure to do this in person for the very, very first time because we've had, some pandemics. And it's also an extreme pleasure to welcome Professor Sonia Seneviratne, who's not only one of the top climate scientists in the world, but also a friend, actually. So it's particularly nice to be able to welcome her here. So Sonia started her studies here at UNIL in biology, but then quickly moved to ETH and then did her master's as a part of her master's at MIT in climate and earth sciences. Is that correct?
Environmental physics.
In environmental physics. And then did her PhD at ETH, and I didn't remember all of it. I'm remembering one thing out of two. So did your PhD at ETH, and then?
Well, I finished 2003, and I did my postdoc at NASA.
Postdoc at NASA, that was the one. So postdoc at NASA, and then came back to ETH as a professor in 2007. She's been involved in more IPCC reports and IPCC processes than I can count. So pretty much all the major ones. Especially the one on 1.5 degrees is a very major role, and AR5 as well.
No, not AR5.
AR5. Okay. So so has really been contributing massively to the science of extreme weather events and probably being able to model it, being able to have some kind of geographic resolution on these topics. And we're just really, really lucky to have her in Switzerland and to have her here with us. And if you saw the documentary on, there was a Temps Présent documentary last week on the ETHZ, Sonia plays a starring role because she is shown a clip of a particularly unpleasant Swiss politician saying particularly unpleasant things about her in a live forum. And she manages not to get upset on camera, so very impressive. So, thank you, Sonia.
Thank you very much, Julia, for the kind introduction. So I have to change the presentation. So I hope everything is can be well seen. That's fine. Okay. Yeah. Well, thanks a lot to Julia for the introduction, and thanks really for all the colleagues here at Lausanne for the invitation. It's always a great pleasure to be here. And as Julia said, I actually started my studies here. I was born in Lausanne, and so I mean, it's a place I really like. Je peux bien sûr aussi parler en français. Je serais contente de répondre aux questions en français aussi. Mais bon, on m'a demandé de faire la présentation en anglais, donc je le ferai en anglais. So in this presentation, I speak about changes in climate extremes, and I want to show you why every year matters. And I would say this is something we have known for a long time. Already since the 1.5 report at the latest, where we really started saying it's really a matter of a few years to get us on track to 1.5 degrees. So I want to start with this picture, which shows that this summer, and that's just one example of several events that we have experienced around the world. While in Europe, we had a very extreme summer, very strong drought. This is a picture of the Loire River. You see it was almost totally dried out. And there has been some statements suggesting that it was likely the driest summer in 500 years within Europe. I include also a few other pictures. I'm sure you have seen the pictures of the fires across Europe. This is a fire in France. So actually in terms of France, of the fire, there is the data that is collected by the Copernicus project, which shows that we have had the highest burnt area this year since the start of the measurements in 2006. There have been also a lot of excess deaths across Europe. Just in Switzerland this summer, there was 1,600 excess deaths. By the end of the summer, this cannot be explained by COVID. And then this picture is showing that, I mean, it was both hot and dry. And so, for instance, there was very extensive melting of glaciers at this location, 6 meters of melt along this summer. So one question I got once was, when do we see that the climate crisis is serious? And I thought, well, probably it's a good question. And the answer to this is we see the signs now. I mean, it's an emergency now. It's no longer a problem we have to face in the future. It's a problem we are facing right now. And so I've mentioned the drought in Europe, but here I'm including a few other extreme events. We have really expansion just in the last 2 years. For instance, the Canada heat wave at temperatures of 49.5 degrees. It's a latitude that is about the same as here. We have seen also the flooding in Germany. Many people died as a result of this event. It was associated with very intense precipitation. And this summer also, for instance, there was a flooding in Pakistan with 1/3 of the country, which was covered by water. And there would be so many more to mention. So first question I want to address is, what is the contribution of human emissions to change in these extreme events? And also maybe even the most important part, how can our decision affect future changing climate extremes? So what can we do to avoid that the situation gets much worse? And you know, which influence do we have actually? So I will speak mostly of some conclusions of the IPCC report. Afterwards, I will also present some results from our research group. So you have seen certainly this report. That's actually a 3-part report. The first part is this part here, which is dealing with a physical science basis. I was coordinating one chapter dealing with climate extremes. You see here pictures of all the contributors. So it's really a collective work. We had about 234 people who contributed to it. And I should say I also presented some of this at EPFL a few months ago, but I provide a bit more detail here also on my research. So about the chapter on extremes, I coordinated that chapter together with Subin Zhang, a colleague from Environmental Canada. And so it's the first time there is really a full chapter dedicated to extremes, one of the larger assessment reports from IPCC. So there had been a special report from IPCC dealing with extreme events and disasters where I had been involved, and which was released 2012. There we had a chapter, but it was not yet actually in AR5. And most of AR5 was based on this special report. Of course, there were some other really important reports. Included, for instance, the Working Group 2 report here and Working Group 3 report. And obviously, several people here also have been involved in those different IPCC reports. So Julia in Working Group 3, Samuel in Working Group 1, and I hope I'm not forgetting more people, but in any case, Switzerland was well represented in the contributions to this report. So I'll focus more on Working Group 1, but I also mentioned some conclusions from Working Group 3 and Working Group 2. So I want to start first with what we know in terms of observed global warming. I think this picture does show very clearly that what we are experiencing right now is really outside the historical data that we have had so far. So you see the evolution of temperature and the observed measurements show that basically since the middle of the 19th century, we have a very clear increase of temperature. And so in the last decade, in 2011, 2020, we had about 1.1 degree of global warming compared to the second half of the 19th century. This temperature level is unprecedented in more than 100,000 years. And to me, I'm always shocked by this number. I mean, you have to just imagine the history of human development and human civilization. Agriculture started about 10,000 years ago. And so all of these developed at temperatures that were lower than now. I mean, if you think about this, it's quite striking. And clearly we are doing an experiment of which we don't know what the outcome will be. So the largest part of this warming is irreversible for several hundreds of human generations. because CO2 stays very long in the atmosphere. It stays several hundreds to thousands of years, a large part of it, which means that even if we were to stop all emissions, basically temperature would more or less stabilize at the level it is now. So I think that's an essential issue with the climate crisis, which is that if we were to stop our influence, it's not just going to go back to what it was before, it's just going to stabilize at what we have right now. The best estimate of the contribution of human emissions to this warming is actually all of the observed warming. So it's about 100% of the warming with some uncertainty around it. But the best estimate is actually that all of the observed warming is due to our emissions. So it's not, as a contributor, it's basically our emissions which led to that. Here, I'm just showing some record of CO2 concentration. For this article in New York Times, which says that we reached the highest level in human history, and this is more or less the headlines we have every year. You see here, basically the evolution of CO2 concentration clearly against this increase year after year, which is a bit disturbing, because you do see, we have known for a long time, actually, this documentary from Temps Présent that was mentioned was also about this, the fact that we have known for so long already in the 80s, basically that we have a relationship between CO2 emissions and global warming, but this didn't change, the outcomes that CO2 continued to increase because we continue to have CO2 emissions. And so this year we have reached for the first time 420 ppm. Now, the reason for the increase in CO2 is really a no-brainer. We know what is the reason for that. It's mostly burning of fossil fuels. So it's burning of coal, oil, and gas. And we know also that these emissions not only have continued to take place, but actually have been increasing, as you can see here. In addition, land use change also plays an important role. Deforestation also leads to CO2 emissions. But I tend to say, when you see this picture, that the problem, of course, the repercussions on society are very complex, but the problem itself is not that complex. It's basically about getting rid of a consumption of fossil fuels. If we have no more burning of fossil fuels, we have got rid of about 9 out of 10%, 90% of the problem. So basically, I think if we have to keep this in mind and just think, okay, the main problem is fossil fuels, we have to get rid of. Now, about the relationship between cumulative CO2 emissions and global warming, this has been established for a long time. There was a similar figure in AR5 in 2013. You see here, basically how much CO2 emissions we have had in total since 1850. And here you see the global warming. And so basically what we have is an almost linear relationship. The more CO2 we put in the air, the more global warming we have. And so that's valid for the observations, which you see in gray, and also for the projections, which means that we know also that if we want to stabilize global warming at a given level, then it means that we have a basically limited budget of CO2 emissions. So really this main point, which is that every additional emissions of CO2 lead to additional global warming. So any additional burning of fossil fuels mean that we have additional global warming. It also means that if we avoid any emissions, we avoid some additional warming. And in terms of the relevance to 1.5 degree, which was the aim set in the Paris Agreement, you see that we have a very limited budget here in light blue that is remaining. Of course, this budget is getting smaller and smaller year after year. So now I say a few words about changes in climate extremes, and that's based on our chapter. We looked at a range of extremes in our chapter, temperature extremes, heavy precipitation, floods, droughts, storms, and compound events. And one main conclusion was that the evidence is strengthened. So compared to AR5, that was 2013, I would say that's one of the areas we have the most development in recent years, because we have had more research, but also more evidence, and simply some of the additional evidence is because we have had more events that took place. So we have had events that just showed how strong the impacts are on extreme events, actually including events that we cannot explain without our influence on the climate system. So one of the main conclusions is that human-induced climate change is already affecting many weather climate extremes in every region across the world. That's an important message. It's not really, there are some hotspots where we have strong changes, but really every region is affected and nobody is spared. And the other important message is, again, that we can start to attribute single events to human-induced climate change, where we say, for instance, are more probable because of human-induced climate change. The events I mentioned at the beginning, we know all of these are made more probable because our influence on the climate system. But also some of them, we say they are so unlikely without our influence. Basically, we can basically attribute them really totally to human influence. That was, for instance, the case with the heat wave in Canada, which was so extreme, you can really not explain it without our influence. Now, these maps here show our assessment, so from our chapter, where we have, based on the literature, evidence of increase of observed increase in hot extremes, extreme rainfall or droughts. And that's really this message that we see that no region is spared. Also, the hexagons are showing different regions of the world, and you see that all region is affected in some way by those changes in climate extremes. An important point is that West Central Europe, where Switzerland is, this is hexagon here, is actually one of the hotspots. So in West Central Europe, we have at the same time an increase of hot extreme. We have an increase in extreme rainfall. We have seen it, for instance, last year in Germany, but also partly in Switzerland. And we have an increase in droughts, as we have seen this summer. So these are observations. So that's tendencies that we have already observed. Now, specifically for Switzerland, often shown this figure from Meteo Suisse, which is showing the mean warming in Switzerland. So each small Switzerland map is showing a temperature anomaly in a given year, and it's ranged by columns. So basically, here you have 2021, and these are different decades, and you see very clearly our temperature has been increasing decade after decade, and that in the last 3 decades we had a very strong warming. And the warming in Switzerland is actually quite strong. It's more than 2 degrees, so it means we have about twice the level of global warming. So we have about 2 times the level of warming compared to the global average. And that's another important point, that when we speak of this global warming levels, this is average over land and ocean, but actually the ocean is warming less. So it does imply much more warming in many regions, including Switzerland. Here I have included a bit new statistics that were published in Data Science Saga, but also based on Meteo Suisse data. It's a different organization of the data. So here you are moving in time, and that's the last decade, including 2022. And so it's showing the anomalies of June, July, August, summer temperatures. And what you see is that in this decade, so basically from 2013 to 2022, we had about 4 summers, which were really extreme, actually even 5. And the 5 of the summers, which are shown with the ranking here, happened in the last 20 years. So again, I mean, we just see that, you know, these extreme events just happen more and more frequently. And actually, in this article, there was a scientist from Meteo Suisse who was cited and was saying this summer in 2022, it's a 100-year event. Because if you look at the statistics we had in the 20th century, so up to 2000, there was never such an event. But the point is, it's not only this event. Again, in the last 20 years, we had 5 summers which were 100-year events. I mean, it just gives the scale of the changes. And this is at 1.2 degree of global warming, and global warming keeps on increasing. So these statistics are going to get worse in coming years. Now about heavy precipitation, there is also a very clear signal. So of course, with increasing temperatures, the air can include more moisture, which means that when you have rain, so you have more total amount of water. And these are statistics also from Meteo Suisse at all stations where you have an increase in heavy precipitation. These are shown in blue. Field circle means that you have a very strong signal. And again, here, I think it's obvious that the dominant signal is this increase in heavy precipitation. And there have been a range of events that happened, even here in Lausanne, for instance, 2018, a massive flooding in the train station. So now about the future, what should we expect? And in the end, that's also, of course, what we care about. What can we do now, and how do our decisions matter for the future? And I would say that's where also the data comes from. It's the future that we'll have will depend on our decisions, of course, in the coming decades, but also in the coming 2-3 years, because we are really at a crossroad. So here I'm showing the projected changes in mean global warming in different scenarios. Those that we have in the IPCC are six report. And you see the projected warming first in the near term, so about 2030. And you see that in all scenarios, we have about 1.5 degrees. So the point is, this aim of 1.5 degrees is just the minimum we can have. It's going to happen. We are, as mentioned, at about 1.2 right now. We had 1.1 the last decade. 1.5 degree we cannot really avoid because of the emissions we have already had so far, and those that are basically built into the system. Now, what will really matter is what happens afterwards. So, for instance, by the mid-century, and there you already have quite a strong divergence. You see that in the lowest emission scenario, we're at about 1.6 degree, in the worst scenario, 2.4. And then at the end of the centuries, we could go back to around 1.5 degree in the best scenario, and the worst scenario at about 4.4 degrees. And well, this shows clearly that the decisions we take now, and I'm going to show the different emission scenarios do matter what happens in coming decades. So here, these are those different emission scenario. And so what you're seeing here is how much emission of carbon dioxide is in the scenario for all those 5 scenarios. I think the really important point again is this fact that we're at this crossroad. It can go in many different directions. So if we really want to limit global warming to 1.5 degrees, we need to decrease immediately our emissions. And we need basically to halve emissions until 2030 and get to zero as quickly as possible. But it's not going to be imposed by outside circumstances. If we want to, we could burn a lot of fossil fuels. There is still a lot of fossil fuel in the ground. So it needs to be an active decision that we don't want to burn it, because we could also follow this scenario if we want to. Yeah. Now, there is only one scenario that is compatible with the Paris Agreement's aim, so well below 2 degrees stabilization and pursuing efforts to stabilize at 1.5 degrees.
Yeah, put down the volume.
I'm not sure what. And so this only scenario is this one in light blue. And again, that's what I mentioned before. In this scenario, you have a halving of emission until 2030, getting to net zero very quickly. And I go back to this later. Now, how does this relate to changes in extremes? Actually, what we find is global warming is well related to changes also in regional climate and also including extremes. So we see with increasing global warming, with an increase in the frequency and intensity of many climate extremes. That's a case of hot extremes, marine heat wave, heavy precipitation, agricultural and ecological droughts in some regions, and proportion of intense tropical cyclone, which is the case now of the high-end tropical cyclone. In general, we have already much higher risk at 2 degrees of global warming compared to 1.5 degree, including some irreversible impacts. And here I'm just showing some statistics for the heat waves, how they change as a function of global warming. So we may take a hot extreme that would have happened once every 10 years without human influence on the climate system. So this event would have happened about once every 10 years. Well, such an event would happen now 3 times every 10 years. So it means it's 3 times more frequent. That's average statistics over land. At 1.5 degrees, about 2030, it will happen 4 times every 10 years. At 2 degrees, it will happen 6 times every 10 years. And of course, if we go to 4 degrees, basically almost all summers would be that extreme. So I think you see very clearly that the level at which we might be able to stabilize global warming has a direct impact on which, for instance, type of extreme we expect, how frequent those extreme events will happen. Now, you could have similar statistics also for precipitation extremes and droughts. But one point I really want to highlight is the fact that we have multiple threats at the same time. I think that's something that has been really underestimated in the past. It was a topic that for the first time we addressed in the report, both in the Working Group 1 report on physical basis, but also in the vulnerability report, the Working Group 2. The fact that we need to consider those multiple threats, so that basically every region is affected with increasing global warming by multiple changes in climate extremes. And we also basically refer to those changes as compound events. For instance, the fact that you can have hot and dry event at the same time at the same location. So many regions are projected to experience an increase in the probability of compound events with higher global warming, and this includes concurrent heat waves and droughts and increased fire weather conditions. We have just seen this summer. So this hot droughts is basically something that is clear in the literature that is getting more and more frequent, and it is additional. So the impacts are not additive. The impacts are not equivalent to the impact of the heat wave plus the impact of a drought. Because once you have at the same time hot and dry conditions, for instance, you have more impacts on plants because it's more difficult for them, for instance, to survive. It has a distinct drought impact. So it's already dry, but you have very high temperatures. There is high demand for evapotranspiration. So it means more pressure, more stressful vegetation. You also have more risk of fire weather conditions. And as I've said this summer, we've seen this very clearly. We also have more risk of compound flooding. So this is flooding in coastal areas. There you have the combined effect of the increase in sea level and increase in heavy precipitation, either from normal precipitation event, but also associated with tropical cyclones. And so the two effects together lead to much more risk of flooding than the risks associated with only one of the two elements. Another point which personally I think is the most concerning is that with increasing global warming, we have also more risk of having extreme events at the same time at different locations. And we see that, for instance, one possible impact could be on food security, because you have more risk, for instance, at 2 degrees that the food producing areas are affected at the same time by climate extremes than at 1.5 degrees. So this could mean that you have food production shortage globally, and of course it would have massive global impacts. Now, I think it was discussed already in the spring in combination with risk from the war in Ukraine, but we see that those risks increase with increasing global warming. So here I want to show also some assessment from the IPCC special report on land, which is showing some assessment of risk. Yellow means moderate risk, red means high risk, and purple is very high risk when you basically reach a limit of adaptation. And this assessment here is for wildfire damage. And so you see the increasing risk with increasing global warming. So at 1 degree, you are in the moderate risk. So we have an increase in fire weather season. That's what we are experiencing right now. At about 1.5 degrees, so quite soon, we will be shifting to high risk. And so for instance, above 2 degrees, we would have about over 50% increase in the air burnt in the Mediterranean region. And then above 3 degrees, we get to very high risk, with about over 100 million people additionally exposed. And here about the food supply instabilities, it's also from the same report. You see that at 1 degree, we are still in this moderate risk, but actually we are getting very soon in the high risk range, where we could have periodic food shocks across regions. And at higher levels of global warming, we could have sustained food supply disruption globally. So I think you see here are just, small increase in global warming do matter a lot. It's not about only projecting what is happening at 4 degrees, moving from 1 degree to 1.5 matters, and 1.5 to 2 degrees as well. And it's the same case for a range of other extremes, also species extinction. So I don't have the time to discuss all those impacts in detail, but this is the assessment from the Working Group 2 report from IPCC, which provides basically a synthesis of changes in risk for a range of categories. So the RFC1 is for unique and threatened systems, so that's more associated with species extinction. And you see, again, that already now at 1 degree, we are at high risk. For extreme weather events, our chapter authors, several of us contributed to this assessment. We assessed that we are shifting actually also to high risk above 1 degree, around 1.5 degree. And for instance, large-scale cellular events are tipping points where you see that you start to have an increase in risk around above 1.5 degree. So this was one conclusion of the IPCC Working Group 2 report, which says that near-term action that limit global warming to close to 1.5 degree would substantially reduce projected losses and damages to human system and ecosystems. But I think it's also important to realize they would not eliminate them all. I think even though 1.5 degrees is the best scenario we have, and we should do everything we can to achieve it, this is not going to be a safe climate. And so I wanted to just mention a few words also on this. For instance, here, based on this article I did with colleagues who were involved in the 1.5 degree. So here what we looked at were different possible climates that would be consistent with the 1.5 degree mean global warming. So again, we're speaking of a mean global warming of 1.5 degree, but locally you can have different types of ways in which it is realized. And so here at each location, we look at the projected 25th percentile, so the conditions which have only 1/4 chance of happening, but the lowest quartile, and this is the highest quartile, so the 75th percentile. So those maps are not showing any conditions in a single year, it's showing at each location what would be about those projected changes. But I think we see, so that's what would be consistent in any location with 1.5 degree of global warming. And clearly we see that extreme condition could happen. That's already what we're experiencing right now. So for instance, if you focus here on the hot temperatures, you see across Europe and Eurasia and part of North America, we are around temperatures anomaly of between 3 and 5 degrees. Of course, this is fully consistent with what we're experiencing right now. And that's only the 75th percentile. Of course, if you look at the probability of the events that could happen with 10% probability, it would be even worse. I also wanted to show regarding these impacts, the fact that already now, present climate is already dangerous. I mentioned it at the beginning with extreme events that recently occurred, but we have data to show that, for instance, also from the health research community. So that's a paper from a colleague from the University of Bern, Anna Vicedo-Capera. She looked at how much of which percentage of the people are dying during heat wave, which of those deaths can be attributed to human-induced climate change. And she found that about 1/3 of all heat-related mortality can be attributed to human-induced climate change, also in Switzerland. So you have statistics here. In Switzerland, it's also about 1/3. So I think we can clearly see that people now are already dying of climate change. They're already dying because of emissions that have taken place and are still taking place right now. And actually, the health community is one area in which climate change is starting to get much more attention. There's been quite a mobilization, for instance, of health journals. This was a statement that was done by about 230 journals in the health communities, warning that 1.5 degree of global warming would be catastrophic for health. So they are not saying 1.5 degree would be a great scenario. It's already saying 1.5 degree would be catastrophic, and obviously more than that would be even worse. And I think there is more and more evidence on the health side that, again, there are really strong consequences. I think another conclusion that was interesting from the statement of these different journals was that they said also from, if you want, cost-benefit perspective, it's probably not the best way to look at this, but if you just look at how many health impacts associated with other effects of CO2 emissions, the greenhouse gas burning, you would have better air quality if you don't burn fossil fuel, and better air quality alone would realize health benefit that would easily offset the global cost of emission reduction. That is something to keep in mind. So in any case, I think we have already quite high warming, and we are close to this 1.5 degree limit. I'm also always showing this. We have to stop, and yeah, definitely the more we wait, the more we have to stop. And here I'm showing what are the emission scenarios that are consistent with this 1.5 degree aim. That's actually already from the 1.5 degree report from 2018. The numbers are very similar in the latest report of IPCC, but I think it's important to realize those numbers, we have had them since 2018. We have known this for several years. So stabilization to 1.5 degree requires change, which are unprecedented in terms of scale, because we need to have basically this massive reduction. We need to follow those blue scenarios here. So the first part is to basically stabilize global warming to 1.5 degrees. We would need to have emission until 2030. We have only a few years for that. So we need to reach 50% of 2010 emissions until 2030. Then we will need to reach net zero CO2 emission at the latest in about 2040 or 2050. And 2050 is generally a number we read in newspapers, but I think we should just be aware this gives us only 50% chance of achieving this aim. If you want to have more chance, for instance, 2/3 chance, we need to get to net zero in 2040. Finally, we also need some negative emissions. You see the emissions get below zero. So in those scenarios, it's already assumed we will be taking some CO2 from the air, either through technological approach or, for instance, afforestation. But there are some concerns there, and I say at the moment would look more like 10% of present day emission. So we need to do it, but I think we need to be realistic about what can be achieved with that type of approach. Here I include the statistics that were published in Carbon Brief regarding the current commitments of different world nations in terms of CO2 emissions. So here you again have the CO2 emissions and what are the trajectories that would be needed for 2 degree or 1.5 degree in 2030. And so we have these huge gaps there. There is a lot of promise for 2050, but for 2030, the current commitments would bring us to about a stabilization of emissions. But obviously we need to reduce emissions. And so we are very far from the trajectory that would be needed for about 1.5 degree. So we are not on track at the moment. The current commitments would bring us on trajectory about 2.4 degrees, so not necessarily 4 degrees, but still 2.4 degrees, about twice the warming we have now. We already have a huge amount of impacts right now with 1.2 degree of global warming. So just imagine what this implies. So every year matters also because you have lock-in effect. I think that what we have had in the past. The point is we are moving on this trajectory. And of course, the more we emit, the more difficult it is to get to this aim. Because if we had started in 2018, when we had first those numbers from the IPCC report, it would have been a much less steep trajectory. Now, the more that we wait, the steeper it gets and more difficult it gets. But still, generally try not to be too negative. So we say, yes, I think we can do it. And obviously we should do it. And so I try to show a few points here regarding what we could do. Basically, again, as I said at the beginning, the problem is not that complicated. The main issue is the consumption of fossil fuels. So what we need to do is just not use any more of these fossil fuels. So no more use of coal, oil, and gas. For the energy demand, we need to shift to renewable energy. We need to have clean electricity. We need to have an electrification of energy use, and of course, also less energy demand. Julia is a specialist on this area. She can certainly say more on this. In any case, I think the important point is this part of the equation should be about representing 90% of the reduction of current day emissions. That's the main thing we have to focus on. Now, for about 10%, we can imagine taking up CO2 from the air, for instance, through afforestation, through technologies, also maybe new synthetic fuels that would be more like a neutral use of fuels. But in any case, this is about 10% of the current day emissions at most in the scenarios from IPCC. And at the moment, we are very, very far from this number. We are well below 1%. So I think in the newspaper, when you see the attention that is given to this type of solution, it's really not proportionate. What we should focus most on is this energy transition here at the top. I'm showing here. So I say a few words about emission in Switzerland, and then basically, where are we right now? Where we are close to the world average in terms of emissions. We have about 4.4 tons of CO2 per person. I took the numbers for 2019 before the COVID crisis. But we should be aware that we have a lot of emissions that we are inducing through consumption. We had 14 tons CO2 per person, and we were at number 15 worldwide. It's shifting, but it's around this number. So yeah, we're doing really bad on this side. Now, we could ask ourselves, especially now with the geopolitical dimension, we are not a fossil fuel producing country. I mean, it seems a bit absurd to be so dependent on these fossil fuels. I mean, we would have advantage to become independent of fossil fuel producing countries for geopolitical security, especially when you see from which country we are importing fossil fuels. I think this we cannot ignore. Another way we can have quite a bit of an influence in Switzerland is through the world financial markets. So actually there, the financial market in Switzerland is very powerful. Probably we could have quite a bit of an influence there, also through banks or pension funds. Finally, I do hope, I think speaking at universities that we do see ourselves as an innovative country. So I think we could show the way in trying to be, among the pioneers rather than among the laggards. So in terms of the emission in Switzerland, 3/4 of our emissions are due to oil, so petrol. Again, here, if we manage to get rid of this dependency, we get rid of a lot of the problem. 18% is gas. This has been thematized a lot. And so if we get rid of our dependence on gas and oil, again, we have really very few remaining emissions. Before I finish, I wanted to say a few other words also on the question, for instance, of climate justice. I know we have quite a bit of time for questions afterwards, so maybe that's a topic we want to discuss. And certainly one issue in the climate crisis is that the most affected persons have contributed the least to the climate crisis, the poorest nations, but also the youngest people. I mean, if you think that emissions are mostly due to emissions that have been done in the past, and of course, younger people just have to live with what we have done in the past. In terms of the question of climate justice between countries, there are those numbers from Oxfam, which shows that about the 10% richest people have contributed about 50% of the emission, while the 50% poorest have contributed only 10% of the emissions. On this generational inequities, we had a paper led by Wim Thierry that published in Science last year, which shows how many extreme events a person would experience in their lifetime, depending on the year of birth. And so here, for instance, it's change in global warming on this axis, and here that's the year of birth. And you see a baby that was born in 2020 is going to experience about 30 times more heat waves than somebody who was born in 1960. So again, it's about, of course, somebody who was born much longer time ago is not going to experience this as very affecting for their lifetime, while somebody born now will experience it like this. So I want to finish with the question of, could things be worse than we expected? Maybe not a good news, but it's also a question that is often asked. And I think the answer to this is yes, possibly. So we have to recognize, I mean, there's always some question on this, to which extent do we trust our models and our science? There are uncertainties in climate models, and I would say this increase as we move further away from non-climate conditions. So to me, uncertainties is not a reason not to act. I mean, maybe in the past when you said, we are not sure we see something in observations, it could have been an argument, but now what we are saying in terms of uncertainties, we don't really know, of course, what is exactly the climate going to look like at, for instance, 4 degrees. We don't have an analog to look at, but this means probably we want to avoid and not find it out for ourselves. Yeah. One issue personally I'm concerned about is that the models behave very linearly. So what we find is a lot of the relationships are very linear, but it does help to understand the problem. It shows in observation in models. That's what I've shown before. This global warming basically is more or less a linear function of cumulative CO2 emission. Seems to work quite well based on observation. That's what models are showing. Here I'm showing another analysis from a paper we have done with a range of colleagues where we look at change in extremes. So the temperature level is a function of global warming. And also here it was fairly linear. So, I mean, it does help to do projections because we find that our models are working, but I think we could ask ourselves, is this exactly what we expect? Can we expect also some non-linearities in the system? So the literature, both in the IPCC and also, for instance, there was a recent paper that got quite a lot of attention. The science shows increasing risk of hitting tipping points, global or also on regional scale, with increasing global warming, with higher risk above 1.5 degree to 2 degree, but it's highly uncertain. I think we should say that. But again, the further we go from conditions we know, the more difficult it's going to be sure of the future. So one topic personally I'm very concerned about is the effect of droughts on the carbon cycles. This is from research in our group. There was a paper led by Vincent Humphrey, who did his PhD with me a few years ago, and actually was a student from Lausanne as well. And here we looked at the relationship between variations in water cycles, so water storage on land, And here's a CO2 growth rate. So how much CO2 is varying from year to year. And you see here an almost, again, linear relationship, but that's based on the observation. That's not based on the model. Very clear relationship, very high correlation. But then if we compare, I don't have the numbers here, but we compare the correlation we have in those observations with, for instance, correlation we have in models. And this cross means that the correlation in models, there is a negative correlation, but it's not significant. So it suggests actually that the models are underestimating this feedback. So the idea is when you have more drought, plants are more stressed, they take up less CO2, or maybe they die. It means you have more CO2 in the air. And well, this is something you see in observations, the models seem to underestimate it. So this certainly has some implication, could have also some implications for our low emission scenario, which assume a lot of afforestation, for instance, or BECCS, or bioenergy with carbon capture and storage, because the idea is, okay, we want to try and take up CO2 by planting, for instance, trees, or having more bioenergy. But the problem is, again, if plants are very sensitive to drought conditions, possibly this CO2 uptake would not be realized. So to which extent could extreme events actually affect those projections? I think is a really important point. And generally, those extreme events are not included in integrated assessment models. So those scenarios could be too optimistic. And I'm showing here one example of scenarios of change in land cover in different integrated assessment models. So these are the models computing scenarios, emission scenarios. And you see some of them for 1.5 degree have a huge amount of afforestation here. So blue means more forest cover. But again, the question is this realistic? You know, we have just had massive fire in Europe. Then we have massive fire in Siberia. I mean, is all of this forest cover going to be realized? I think that's a valid question. So to address this, in our group, we have just worked on a new development that was led by PhD student Leah Boy. She just finished, and she developed a simulator for Earth system models. It's a simple statistical tool where we emulate the regional response of mean temperature. And now we have also a new development from Yankee Kai, a postdoc in our group, extending this to temperature extremes. And so here you see the evolution of this regional temperature in the model. And here there are different emulations. And the idea is that it's a tool that is computationally very cheap. And we could possibly couple it to integrated assessment models so that they can integrate the feedback of changing extremes in the computation of emissions, for instance, where they compute changes in forest cover. So it's something we are just working on right now. And yeah, we had a small grant in the proof of concept project for that. So I don't want to finish on the two negative notes. So I want to come back to what could be nice in the future. And I think the world without CO2 emissions would be nice. I've said that, you know, if we continue to emit a lot of CO2, there can be a lot of risk associated with it. But in the end, it's a choice we have is between this world where we continue to emit CO2, where we always have more extreme events, possibly more impacts, more uncertainty, or a world where we manage to have a nice life, but without emitting much CO2. And there are numerous co-benefits, including here a picture of Paris without cars. I think it looks quite nice. So there would be less climate impacts and costs for ecosystem and health, as we have seen. There would be also less climate uncertainty. Again, the more we emit, the more we go in the range where we don't know what is going to happen. There will be several further economic benefits for health. So if you burn less fossil fuels, you have also less air pollution. It's better for health, you have less noise. And another way to reduce emissions is having healthy diets, so less meat consumption, having more active mobility. All of this is very good for health. Finally, I think in the last few months, we have seen also getting rid of this dependency on the fossil fuels would mean more geopolitical security, less dependency on autocratic fossil fuel exporting regime. I mean, thinking about whether we want to be rather dependent of democracies, autocratic regimes is probably a valid question. So I come to the conclusions. It is worth limiting global warming to 1.5 degrees. This aim is stated in the 2015 Paris Agreement and confirmed in 2021 Glasgow Climate Pact. And the first essential step is to halve CO2 emissions until 2030. Irreversible damage can be avoided worldwide, so there are impacts everywhere, but there is no return from several consequences. So this whole question of irreversibility is important, for instance, for species extinction, but also vanishing glaciers or sea level rise. The window to act is closing very rapidly. So if we want to achieve this aim in 2030, we will need to decrease CO2 emissions by 6 to 7% per year. That's why I said at the beginning, every year matters. If we want to be serious about this, we need to have very massive decrease very quickly. Finally, a world with no CO2 emissions would be nice to live in. I think doesn't need to be a dystopia, doesn't need to be bad. We can have a nice future. We would have a safer climate, less climate uncertainty, more healthy conditions, and more geopolitical security. And I finish with what I'm often showing, these words was based on the IPCC special report on 1.5 degree. Every action matters, every bit of warming matters, every year matters, and every choice matters. Thanks a lot.